All right. So if you are interested in reviewing for the test for Unit 5, there's a couple things that you want to definitely focus on. So since this was our unit regarding waves, I'm going to kind of start off with the characteristics of a wave here. And I've left it so you can kind of see most of my screen in terms of like at the top where this is coming from. So this is the day 3 stuff, tinkering with a wave. And you can see that we're on slide 10 here. So if you wanted to follow along or if you wanted to look back at those, feel free to do so. First thing, knowing the definition of what a wave is always useful. A wave is just the disturbance that carries energy. Again, we've had lots of examples of that at this point. Um, some of the interesting or important characteristics of a wave are the peaks of the wave. And when we say peak, we could be referring either to the crest, which is the top of the wave, or the trough, which is the bottom of the wave. And these are especially important because they're going to be important for a lot of our other definitions, rely on knowing what peaks and crests or troughs are. So the next one, for example, wavelength is measured from peak to peak. So that could be from crest to crest, or it could be measured from trough to trough. And that would be the wavelength of a wave. And again, we've got the blue arrow and the green arrow kind of showing what that looks like. Either way, you're going to get the same numerical value. The period of a wave is a little bit harder to kind of see on here. Again, moving picture would make a little bit more sense, but it's how long it takes for one whole back and forth motion, one whole cycle. And so if you're on the simulation, if this was running, you'd watch, this part go up to the top, watch it go all the way down, watch it come all the way back up to the top, and the amount of time that it takes to go from the top all the way down and all the way back up is one full cycle and one period. Frequency is the inverse of that. And what we mean by that is instead of looking at how long it takes a single wave, this frequency is looking at how many waves go by in a second. And so in this example, again, you'd be kind of looking at the doorway or the window here and counting how many full waves go through that doorway in 1 second. The velocity of the wave is how fast the wave moves through the medium. Again, waves always need a medium to travel through. String waves need a string, slinky waves need a slinky, sound waves need air, things like that. The amplitude of a wave is measured from the equilibrium or the midline to the peak. So that could be midline up to the top, as is shown in this picture here. So this is midline or equilibrium up to the crest, but you could also measure it from the midline down to the trough. Direction of wave propagation. In this case, the simulation that we've been using, the waves all move from left to right. Again, if you've got that empty window there, they all just leave out through that side. And that's just the direction that the energy is flowing. I always kind of like to think of it, if you're, a surfer catching the wave, what direction are you being pushed by the wave? And that's going to be the direction of propagation. Direction of oscillation is the direction that the individual particles move. So if you just focus on one of these particles in the wave, what direction does it move? And in the case of this simulation, because it's what we call a transverse wave, those particles themselves move up and down, even though the wave propagates or moves to the right. And again, we've played around with that simulation quite a bit, so you guys are kind of familiar with that. So this is kind of the definitions, was all on sort of that day 3 stuff that was pretty important. The next thing we'll kind of take a look at is off of the day 8, 9 stuff. And this is where we were kind of just recapping and thinking about what we were doing when we were doing our labs. And so this is right after the waves lab. And we're looking at a couple of things. The first is the relationship for wave velocity. And we realized that the velocity or speed of the wave is constant. It doesn't change even if we mess around with the amplitude, even if we mess around with the frequency or the wavelength. None of those things changed the wave velocity. And so we realized that wave velocity was constant. Now, there are ways that we can, in fact, change the velocity of a wave, and that is by changing the material that it travels through. So if we mess around with something like the tension in a string, that would change the velocity of the wave. But amplitude, frequency, and wavelength do not affect the velocity at all. The next part of that lab that we were doing was messing around with wavelength and frequency and seeing the relationship between those things. And we realized that they have an inverse relationship, meaning that if we double the frequency, it cuts the wavelength in half. And so we were able to then put those two equations together and get this combined equation here, that wavelength equals wave velocity divided by frequency. And we can see that that velocity, again, remember, is going to be constant. It's going to be wavelength times frequency if you move the equation around. But that velocity is constant. And so taking that value and dividing it by the frequency, we can get the wavelength. And if we doubled the frequency, because it's on the bottom there, we're dividing by twice as much. That tells us why the frequency has the impact that it does on the wavelength, and that doubling the frequency is going to cut the wavelength in half. There's some practice problems that you could take a look at. And again, it's talking about the packet page 6 stuff. And so I'm going to go ahead and kind of take a look at the packet stuff. So again, this is just in the Unit 5 drive, right? So I'm just scrolling around here for things, and we're looking at this packet for waves and technology. And I'm down over here, and we're looking at page 6 of 12. And this is the worksheet that a lot of you guys did in class. Shaking the slinky with different tensions. Again, none of the other parts are changing. We're only changing the tension. And yes, the tension does have an effect on the velocity. So low tension is a slow wave. Medium tension is a medium wave. And high tension should be a fast wave. And so we know that as tension increases, velocity increases. So you could have a proportional line here, nice diagonal proportional line, or you could have a quadratic. Both of those show that as tension increases, velocity increases. We would need to do a little bit more study to figure out which relationship it is. But we know it's one of those two. And again, in words, as tension increases, velocity increases. This second situation here, we're told the velocity of the wave, and we're shaking it at different frequencies. Great, but frequency doesn't affect the velocity. Just like we're giving it different names, or it's a different colored string. It doesn't matter. It's not going to affect the velocity. So our velocity of 100 is constant. Velocity 100. Velocity 100, 100, 100. And we get that horizontal line that we saw in the slides earlier. Again, wave velocity not affected by frequency. In words, we would say that as the frequency increases, the wave velocity stays the same. Lastly is this relationship with the wavelength. So we know that the wave velocity is 100, and we know the equation is wavelength equals wave velocity divided by frequency. So 100 divided by f, and our f changes, right? So the first one would be 100 over 1, which is just 100. When frequency doubles to 2, wavelength gets cut in half. 100 divided by 2 is 50, and then 100 divided by 5 is 20. And so we have that inverse relationship that we're looking at. So the inversely proportional line is more or less like this picture here. Again, it's always a hard one to kind of draw. Just do the best you can. In words, we would just say that as the wavelength increases, as the frequency increases, the wavelength decreases. Describe what does and does not change the velocity of a wave. Tension changes the velocity, right? Frequency doesn't change the velocity. Wavelength doesn't change the velocity. Amplitude doesn't change the velocity. The next part, again, was all pretty useful stuff. This is kind of looking at labeling. Again, making sure that you know, that was sort of that day 3 stuff, making sure you know how all these things are measured and all the definitions of things. And we have a couple of practice, kind of just understanding the relationship. If we increase the amplitude, what does that do? It doesn't affect the frequency, right? If we increase the frequency, it doesn't affect the amplitude. If we increase the frequency, it cuts the wavelength in half. If we increase the amplitude, it doesn't affect the velocity. To try and figure out what the velocity is, we have to think back to what we know in the beginning. We know that the frequency and the wavelength, if we put those together, we can figure out what the speed of the wave is, because we know that there's a relationship that the wavelength 4 is equal to velocity over frequency. So all we need to do is just multiply those two things together, and we get that the wave speed must be 6. That's the only way that that statement is true. And we would have 6 divided by 1.5 is 4. Yes, that checks out. All right, so that covers that stuff. The other thing worth kind of thinking about is the amplitude modulated light and sound modulated light. And so when we're thinking about that, amplitude modulated light is bright or dim. Frequency modulated light is different colors of the electromagnetic spectrum. So you'd have like red and green. For sound, amplitude modulated sound is loud or quiet. We would call it volume, but it's amplitude modulated. For frequency modulated sound, it's different frequencies or pitches or different notes if you're a musician. So that's an important part for the test. And then again, we're trying to think about what else is going to show up. Well, the same thing that covered that last quiz is kind of knowing how to do these AM and FM conversions with the digital signals. Again, remembering that zeros are sort of the low things, and then ones are the higher things. So if we had something like an electronic signal, zeros flat line, ones would be up high, 0 down low, 1 up high. So it's sort of like the on-off, right? So off for the zeros, on for the 1, off, on, off, 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 on, off. For the AM and FM signals, we kind of like to have a little bit of squiggle in here for the AM signals, so I'll just jump over to a different example that's a little bit better for this. So again, we can see the 0 is just kind of like the normal wave, and then 1 is an amplified wave, right? It's taller. Notice that the frequency is the same, right? 2 peaks, 2 troughs, 2 peaks, 2 troughs, right? So for the AM, we're not changing the frequency, we're only changing the amplitude or the height of the waves. So 1s would be a higher wave, 0's shorter wave. 1's the higher wave, 0's the shorter wave. For FM, notice that they're all the same height. They're all the same amplitude. Because for frequency modulation, the only thing we're messing around with is the frequency of the wave. 0 is your normal, and then 1 is a higher frequency, which means a smaller wavelength. Remember the inversely proportional relationship. Frequency goes up, wavelength goes down. So these waves are closer together. We can fit 4, right? 1, 2, 3, 4 of these crests instead of the 2 that we had before. So we've doubled the frequency and cut the wavelength in half. So again, 0 for the normal one, 1 for the squished together or higher frequency wave. And then 0s and 1s and 0 and 1s. So again, there's a couple of things that you could flip through and practice kind of on your own for these, taking the FM, finding the binary, finding the AM, and practice a couple of these. And these are all in the day 15-16 review. All right, best of luck on the test.